All right, welcome to section 7-3, the number E. Make sure you jot some good notes down on this and, rewind if you need to so that you can come in with some good questions to class because this is going to be new for everybody and it can be a little bit tricky to understand. So the first thing we want to talk about is what is the number E and where does it come from, okay? Because the number E is kind of one of these magical numbers like pi in geometry, but E is probably even more important and more commonly used. So to give you some perspective as to where it comes from, I want to start by talking about some compound interest. If I, let's just pretend, and I won't write down a problem, but let's just pretend I have $100 and I have that in the bank, and let's just say I get 10% interest, and I keep it in there for 5 years. And I'm only going to compound it once a year. That's why I don't have a divide problem in here. I'm just doing once a year. I'll get all my interest on December 31st. I'll get my chunk of interest. And if I calculate that out, which you already know how to do, you will end up with $161.05. But we know that if I don't wait until December 31st, if I don't wait till the end of the year to give you your interest, you can do a little better. Because I could give you a little bit of your interest in January, and it would have the whole rest of the year to start gaining its own interest. And so this is the idea of compound interest. I could have the same $100 and pay you the same 10%, but I could pay it in chunks of 12 and say 12 times 5. So I'm going to pay you a 12th of your interest 12 times as often. And I don't do a lot better, but you will end up with $164.53. So you do a little better because your interest has more of an opportunity to gain its own interest. Now, if a little's good, more is better. What if I paid you every day? What if I paid you 10 cents over 365? Now, we don't do a lot better here, but still a little bit. So 164.86. So, but what if I kept going with this? What if I paid you 1,000 times a year? What if I paid you 10,000 times a year? I mean, I want to pay you as often as possible. It's only pennies, but the more often I pay you, the better you do. Could I pay you an infinite number of times a year? That's the question. And the answer is yes. I could pay you an infinitesimally small piece of interest an infinite number of times a year, and that's the scenario where you're going to do the absolute best. Again, it's not going to be much better. You know, we only do better by a little bit each time, but every little bit helps. So to understand how that works and what this number E is, we're going to play a little input-output game. I'm going to input a number n, and I'm going to input it into the following equation. 1 plus 1 over n to the nth power. 1 over 1 plus n to the nth power. Now, if that looks like the compound interest formula, it should. It's very, very similar. So let's say I input a 10 into n. So I'm taking the 10 and I'm substituting it here and seeing what I get. Turns out I get 2.59374. Okay? All right, let me do it again. I'm going to do it with 100. And if I do it with 100, it will be 2.70481. And let me do it for 1,000 and see what I get. If I input 1,000 in for n, I get 2.71692. And let me do 10,000. So if I do 10,000, I'll get 2.71815. And let's do 100,000. If I do 100,000, I'll get 2.71827. And I'll do it one more time. I'll do 1 million. 1 million, I get 2.71828. Okay, so I want you to notice a couple things here. First of all, I want you to notice that this n kind of represents like my number of payments in my interest. Okay, so it's very similar to that. And so you could almost think of this as I'm paying you interest 10 times a year, 100 times a year, 1,000, and down here I'm paying you interest 1,000,000 times a year. But what I want you to notice is the final numbers. Here I have 2.5, and that jumps to 2.7. So a little bit of a change, 0.2. Notice the next one, it sticks at 2.7. Okay, 2.716. Then it goes to 2.718, and then it stays at 2.718. 2.71815, 2.71827, 2.71828. The change that we see from number to number is getting smaller and smaller and smaller. And it turns out that the bigger we go, this number will approach the number E, which is approximately 2.718. Which is kind of like how we say pi is 3.14, but it really goes on forever. E is the same way. E is we approximate as 2.718, but it goes on forever. It never repeats and it never terminates. So basically, if you want to think of it, this is a little oversimplified, but if I take my compound interest formula and I pay you an infinite number of times, this number E pops out. And so it is very common in exponential functions to see the number E used. Now, I know that's not a proof of why E is going to be a part of all this, but hopefully it's enough to convince you that there's a relationship here between our exponential function over here and the number E down here. They are related to each other. So then the next question is, how do you use the number E on your calculator? And E is so common that just like pi, there is a button for it. You will find on the left side of your calculator a button that looks like this, E to the. And you just use it like anything else. You can do E to the squared if you want, or E cubed. So you have a button for it that you will be using. Now, jumping back to the compound interest. If you want to calculate your interest payment, because remember I have $100, right? I had 10% interest, and I had 5 years. Okay, now if you want to do the absolute best on interest, you will use the continuously compounded interest formula, which is slightly different than the interest formula we know and love. Since I don't actually know how to plug the number infinity into this formula, like where I plug the 365, I've got to have another strategy. And so the continuously compounding interest formula is this. Amount in your account equals P e to the RT. And that's, of course, your principal, your rate, and your time with the number E. So if I want to use this, it's very easy. Here it is. The amount in my account, I started with $100 of principal, the number E, to the 0.1 times 5. That's P e to the RT. Okay, now if you've ever used the shampoo PERT, I call this the shampoo formula because PERT is a brand of shampoo. But if you've never heard of that before, ignore it. I'm old. And what we end up with is we end up with our best possible interest. And this right here is exactly how I would type it in my calculator. And let me do that real quick so I can tell you how we do. So P e to the 0.1 times 5. And I end up with $164.87, which is basically a penny better than I had with daily compounding. I was at 86, now I'm at 87. But this is the best possible interest we can get. Okay, so continuously compounding interest uses this magic number E. Now, the thing about E is that it will show up in other kinds of exponential formulas too, because the reality is, take a chemical reaction in chemistry class. Chemical reactions don't just happen 4 times a year or 365 times a year. They happen continuously. And so you'll see scenarios and models and problems that use this E. And here's an example. I just made this problem up, but annual sales of VCRs from 95 through 2005 can be modeled by this guy, okay, where T is the number of years since 1995. So if I plug in the number of years since 1995, it'll tell me how many VCRs were sold. Probably, I'm just guessing, the number of VCR sales is going to go down, but I could be wrong on that. So it says graph the model. And to graph the model, you know, input, output, right? We're going to input T, and we're going to get Y out. Now, I just pulled some numbers from my graphing calculator. I just put this into the table. But let me relabel my axes here. Let's do this as, we'll do these in 10,000s. So 1 is really 10,000. 8 will be really 80,000. And 70,000 and 60,000 and so on. So I know right away in the first year, I sold 60, let me grab a different color here, 60,000 VCRs, and according to the table on my calculator, again, I'm just inputting this into the graphing calculator so I can get some numbers. In year 1, the sales were about 51,000. In year 3, I'm just going to skip a little bit, they were 38,000, so right about here. In year 5, they were 28,000, so right about here. In year 7, they were about 21,000. And I'll do year 8, they were about 18,000, so about right there. So if we graph this in, you'll notice that we will get exponential decay. Okay? And so we can just see how these VCR sales went down. It uses the number E, but I'm not really doing anything different. And okay, then it says, all right, go ahead and estimate the VCR sales in June of 2001. Okay, well, June is about halfway through the year. So I'm talking about halfway between 2001 and 2002. So I got to think a little bit on this, because this right here was year 0. That's 1995. So year 1 is 96, 97, 98, 99, year 5 is 2000, 6 is 2001, and 7 is 2002. So I'm talking about halfway between 2001 and 2002. So here's 01 and 02 right here. Here's about halfway between them. So I'm going to go up to my graph and go over and see that this is between 10,000, or sorry, this is between 20,000 and 30,000. So I'm going to just rough estimate about, whoops, I'm down here. Rough estimate about 25,000 VCRs based on that graph. So it's the same thing we've been doing before. The model just happens to have the number E in it, not rocket science. So, okay, how do you tell with an exponential model that uses the number E, how do you tell if it's growth or decay? Well, in the last model, we had 60,000 E to the negative 0.5t, and I want you to notice that negative sign there. That negative sign is what caused it to be decay. If that was a positive sign, it would be growth. So, negative exponent equals decay. Positive exponent will be growth. And it's just a little bit different when you're working with these models that have the number E in them. It's just a little bit different than what you're used to. But you'll see a few in your assignment, and that'll help you get used to it. Now, just so you know, in addition to what I've showed you, a couple of other things you'll be seeing in your assignment. I will have you do some very simple problems where you use the calculator with the number E. Like I might just say, hey, compute E to the 4th power for me, just to get you used to typing the number E on your graphing calculator. I may give you some that have some exponent rules, where you tell me e to the 3rd times e to the 4th is e to the 7th. Again, these aren't too hard. These aren't ones that I really want to go over in the video, but they are ones that you'll see that will help you get comfortable working with this new magic number e that is used in exponential models. Okay, so in conclusion, we learned a little bit about where the number E comes from. It's about 2.718, and it's the idea of an infinite number of interest payments, so to speak, but this idea of continuous growth. And we see it in continuously compounding interest, which we have a new formula for now, and we'll also see it in some of the models that we've seen before. So thanks for watching. Please come to class with some good questions, and I'll have some problems for you to do.